Actually, scientists and scholars of all kinds spend most of their academic and professional lives learning, not necessarily in the sense of students that we're talking about most of the day, but in the sense of trying to understand what it is that needs to be known in order to be professionally successful and to understand how work that scientists may do may fit into a broader context. Before I get there, I want to tell you a story. I want to tell you a story about a colleague of mine on the faculty whose name is Pervez. He works in my division. He calls himself a data parasite. What Pervez does for a living is actually to study other people's data. And it's important to get a little bit of background here first. In biology, people had a real revolution about 20 years ago when it became possible to build chips that would have on them information about basically every gene you would want to have on it. And you can use these chips to understand how genes get turned on and turned off as cells go about doing their thing. The information that scientists collect using these chips gets stored in a national database called the Gene Expression Omnibus. So if you're a biologist and you study gene function, you use these chips, you do your experiments, you put your data into the Gene Expression Omnibus, affectionately known as GEO. What Pervez does, he goes out to GEO, and without ever going into a laboratory, without ever killing a mouse, Pervez is able to see the data that are in GEO, searches for particular data sets that are relevant for him, and he elucidates different kinds of genomic signals, and he tests those signals to see whether they help in validating hypotheses that he has about biological phenomena. And what Pervez has done is really some really incredible stuff. He's been able to use information he's gotten out of GEO that other people have collected in their own experiments to identify biomarkers that might indicate when a patient is becoming septic, or when a patient has TB, or when there's a question of trying to distinguish whether someone has a bacterial infection or a viral infection, or to identify when a patient might be rejecting an organ. So here's a guy who has been able to parasitically look at other people's data in public repositories and learn a tremendous amount of stuff, and he's never done what a biologist would consider to be a real experiment himself. But a guy like Pervez can be successful only if the data are out there in some repository, only if there's a way of searching for the data to get what you might need, whether when you get the data back, they're in some sort of a framework that you can actually understand. They have to be self-describing, so you actually know what the experiment was that the investigator did. And they have to be intended to be reused and basically to outlive the experiment, and frankly, to outlive the experimenter who collected those data in the first place. That's the problem. The problem is that most data actually that you find in public repositories are a mess. That most of us in academia view our jobs as to getting promoted, and we get promoted by writing papers. We view the papers that we publish as being the primary object of what we do, not necessarily the creation of data sets. Sponsors will say, well, you've got to create your data sets, you've got to make them public. You can't publish without making your data sets public. But no one really pays us to do that. And really, to create high-quality metadata that a third party can understand is a real chore. Most of the time, what investigators do is they take a bunch of spreadsheets, they fill them out very casually, send those spreadsheets to the repositories who, frankly, are happy to get anything they can. And so the data that exists in public repositories are bad because it takes so much work to actually create good metadata to describe what the experiment's all about. And frankly, it's really hard to ensure that metadata are standardized and searchable and usable. And so that's why Pervez has a hard time, but what he does is really quite dramatic. Put that aside, let me tell you another story. Also, not necessarily as inspiring, and that is, you may remember a few years ago, The Economist had a great cover story. And all of us are sort of in the situation now where there is a lot of conversation about the crisis in science, and you hear a lot about this in the lay literature, where when this article came out, this followed some very high-profile investigations that were reported in Nature, where people in various pharmaceutical companies and biotech companies had tried to replicate what were considered the classic studies in cancer biology, and found that most of the time they couldn't replicate those studies. And worse, they couldn't go back and find the original data that were used to do those studies to actually verify what the original investigators had actually collected and what they had done. And so we're in a situation now where we have data parasites trying to make sense out of publicly available data. We have people concerned about scientific integrity who want to get access to public data in order to be able to make sense out of that. And frankly, what we need at a minimum is to have open online access to data sets, mechanisms to search the data, the ability to annotate those data sets with high quality metadata so we can actually understand what the original investigators did when they collected their data. And we need to control terms in the metadata whenever possible, as I'll say in a moment. And most important, we don't need technology. We need a culture that values the sharing of data, that recognizes that the data that comes out of the scientific laboratory is the principal endpoint, not the PDF that turns into an article in Science. And accompanying all of this angst has been a lot of discussion over the past 2 or 3 years over this buzzword that now is ubiquitous, that scientific data need to be fair. By fair, we mean findable, accessible, interoperable, and reusable. And the notion that we should be able to have our scientific data accessible to us so that they can be available for third parties to study, so they can be available to verify scientific results, all of this is now pervasive in the discourse of the science of science. That's all well and good, but then how do you have fair data in the first place? And let me make a couple of suggestions. One of the first requirements is that we need standard ontologies to describe what exists in the data set completely and consistently. And those ontologies need to be able to be sufficiently expansive to cover the area of discourse for the particular domain, and they have to be sufficiently granular that we can understand what was done in those experiments. Now, unfortunately, I work in the medical school. In biomedicine, we have a long tradition of this kind of thing. Linnaeus did his work in the 18th century. We understand very well in medicine, at least, how to do speciation, and that's very helpful. But also, there have been hundreds of ontologies in biomedicine that have been important. Folks have created something called the gene ontology. Some people have mused that the gene ontology is neither about genes nor really an ontology, but I won't go there. The gene ontology actually is enormously important because it provides a standardized way of talking about biological processes, what happens in organisms, cellular components, where in the cell do these processes take place, and molecular functions, what are the actual molecular mechanisms by which biological processes occur. Gene ontology is so ubiquitous that people can't do biology now anymore without referring to the terms of the gene ontology. In clinical medicine, we have things like SNOMED. SNOMED is a terminology of some 350,000 concepts that describe everything in medicine, from diseases to procedures to all the chemical entities that are important for making drugs for agents that cause disease, for all kinds of infectious organisms. It's just enormously comprehensive, and it's the basis for the electronic medical record systems that are now ubiquitous in the US. I should mention that we at Stanford have created a resource called BioPortal, which basically is a repository of all the world's publicly accessible biomedical ontologies. And the most important thing for me to tell you about BioPortal is that the number of ontologies in biomedicine is just astronomical. There are 737 ontologies in BioPortal. I don't want to say that that is necessarily a feature. I think it reflects the fact that there are so many different groups of scientists who all see the world in a particular way, who feel a need to be able to describe what they do in a particular manner. And therefore, in biomedicine at least, we have enormous numbers of ontologies. And frankly, one of the major goals of BioPortal is to provide a system that looks at the tasks that you want to perform and makes a recommendation as to what ontology might be the right one to use for that particular task. The good news, at least for us, is that BioPortal is being used extensively throughout biomedicine. People in industry and government, and the pharmaceutical industry in particular, lots of academics come to BioPortal. We have a couple million API hits a day, which is, for us, it seems like an enormous amount of people interested in something as arcane as biomedical ontology. But it shows you why it's so important in this area of science. And frankly, what we need are more Linnaeuses. We need more Linnaeuses who are going to create the ontologies that we need for other scientific disciplines, for the humanities, for law, for all the areas of human endeavor right now which don't have that kind of formalization. We're doing really well in biomedicine, but obviously we have to figure out mechanisms whereby we can get the initiative and get the funding to do this kind of work in other areas of endeavor. Back to the issue of fair data. Talked about ontologies being important. We need to be able to describe the experiments that we do in a way that make it possible to understand what the experiments actually achieved, how they were performed, and fundamentally what we can learn from them. And what that means is when we look at experimental data, we really want to know what are the data all about? How can we search for additional data that are like those data? How can we group them into categories? For all that, we need metadata. We need metadata that describe not only the file that we're looking at, but we have to understand conceptually who were the investigators, what did they did, why did they do the experiment, what did they collect, what were their methods, what were their instruments, when and where were the data collected, and for the particular situation, what are the parameters of the data that actually are before me. Unfortunately, the metadata that exists in public repositories right now don't really capture that very well. But we see increasingly scientists responding to the need for comprehensiveness because scientific communities of all kinds, and again, particularly in biomedicine, are talking about what at least are the minimal things that a metadata set should say about an experiment for them to be useful. And so what we see are investigators getting together is proposing that for a particular class of experiment, there are things that you need to say about that experiment for some other third party to make sense of what you've done. And so we see a proliferation of what are called minimal information models, which are basically checklists to make sure that your metadata are sufficiently comprehensive that they have some meaning. And although the biologists are taking the lead, other areas of science are catching up. And you can go to fairsharing.org. You can see a repository not of data, but not a repository of metadata, but a repository of the kinds of standards that people are proposing in science to ensure that their data sets and their metadata descriptors are adequate for describing the kinds of experiments that have been performed. So we have ontologies, we have the beginning of standardized metadata, but we need to make it at least palatable, if not easy, for people who are really thinking in terms of their science and nature papers to be able to easily create the metadata that will allow data parasites like Pervez and people concerned about scientific rigor like NIH to be able to access the original data and make some sense out of them. And for that at Stanford, we've created a system called Cedar. Cedar is the Center for Expanded Data Annotation and Retrieval. We like the acronym. We're at Stanford. We like trees. And so therefore, we think this is a really appropriate way to be moving forward. Basically, Cedar offers an ecosystem, if you will, of how to manage scientific metadata in a way so that ultimately people can learn from those metadata in a more comprehensive and useful way. So in the Cedar approach, scientists are performing experiments and generating their data sets. Community-based groups are getting together and creating the standards for what metadata should look like in particular areas of science. Cedar users create formal templates that allow us to talk about metadata in a reproducible and standardized way. And then the Cedar users fill in those templates every time there's an experiment that needs to be annotated, describing in the context of the template what was actually done to collect the data. And then Cedar stores those data sets and the metadata and makes them available in public repositories. So think of it in terms of a cartoon. We have metadata authors who are creating libraries of templates to describe the metadata for different classes of experiments. We have the people who actually do the experiments, the scientists, who use Cedar to enter into the templates descriptions of the experiments that they performed so that they can be described in a way which makes the metadata useful to people down the road. We actually store our metadata in a repository locally, and I'll say in a moment why we do that. But the main idea is to be able to instantiate these templates, to tie them to the experimental data sets, and to upload those data to public repositories so the world can actually see the data and make some sense out of them. So what does it all look like? Well, Cedar gives you a library where you can manage your library of templates. You can share your templates with your friends or colleagues. You can get templates that come out of standard professional organizations. And it provides a basis whereby you can deal with templates in your particular area of science. If you want to see what some template looks like, here's the biosample human template. That is a template that describes the metadata that investigators use when they upload data sets to a repository called Biosample, and they're looking at human tissue. So we can see that there are various attributes. Each attribute has a value. And the important thing about Cedar is that, unlike the case with traditional metadata in public repositories, Cedar gives you all kinds of drop-downs and other kinds of user interface affordances that make it essential for you to, whenever possible, use terms from standardized ontologies rather than to roll your own. And so the fact here, for example, when specifying the tissue, by making a selection from this Uberon ontology, which includes anatomy and tissue information, we can be assured that the scientist filling in the template will use a term that people down the road will be able to search for and find. More important, we want to make this easy. So for example, here we're entering information into biosample human. We specified that the tissue sample that was studied in this experiment came out of the lung. We haven't specified yet what the disease is, but because we know from previous metadata and we can learn patterns in those metadata, we can say, well, if the lung is the tissue, then there's a good chance the disease is going to be one of these diseases that have migrated to the top of the drop-down list. And the scientists can say it might be lung cancer, it might be chronic obstructive pulmonary disease, might be squamous cell carcinoma, but it's not going to be prostate cancer. Similarly, if we're saying the tissue comes from the brain, then all the drop-downs get reordered. And again, we make it simple using as much of menu tailoring and predictive data entry as possible so that scientists can find it relatively easy to enter metadata that can describe their experiments in a way which is complete, comprehensive, and useful to third parties down the road. And the goal there, therefore, is to make the data fair. And we think Cedar sort of represents one of the first real examples of technology that can make data fair by drawing on ontologies, templates, and community standards the way that I've discussed. What does it all mean? Well, it means for the data parasites of the world, we're in a situation where the data that are now being put into public repositories can be more findable, accessible, interoperable, and reusable. And because those data are cleaner, because the metadata are better descriptors of what the experiments actually were, people like Pervez can actually access those data and do a much better job at their work trying to make new discoveries by learning from the experiments that other people have done in the past. Scientists themselves will be able to learn new things from data by doing a better job of annotating those data, because by having better data in online repositories, they're able to see what their colleagues are doing in a way which doesn't necessarily come through from the Nature paper or the Science paper, but they can see very directly the kinds of experiments that were done and the quality of the data that were acquired. Scientists can actually look at those results and see how the results of other scientists might relate to the work that they're trying to do. The scientists can also use the results from public repositories to be able to integrate their results with other results and perhaps make discoveries that wouldn't be possible otherwise. So in the life sciences, there's a big advantage. And in clinical medicine, doctors, this is not a real doctor, by the way, doctors have the ability to use data that they understand in more concrete ways to be able to do things which right now are really hard. This stereotypical example is a doctor has a patient with a complex problem. The question always is there a clinical trial that's been done that would provide guidance to me so I know how to treat the patient who's in front of me? That requires knowing that there are clinical trials that actually entail interventions that are available to the doctor. That's going to be available by looking at the metadata from those clinical studies if they're available online. But the most important challenge is saying, look, lots of clinical trials are done in the world. I want to find the clinical trials that are done on a patient population that most resembles the patient who's sitting in front of me right now. And that's a hard question to answer. Obviously, the journal articles will describe their patient populations in tabular form, but being able to go to the original data sets, to be able to look at the data, will give doctors new kinds of insight that would be possible that are simply not available right now. And the doctors are probably not going to do that directly themselves. I think all of us will have intelligent agents that will be able to go out to these online repositories and get access to those data and answer these difficult questions. Now, at the same time that the world is working hard to categorize and make experimental data more useful and more available, there's also a big trend going on to be able to formalize the knowledge that might be associated with the data sets that we acquire. And there's a big initiative now throughout basically all of the business community to create knowledge graphs. This happens to be a very small snippet of the knowledge graph that Google has. you can bet that every e-commerce company you've ever heard of has a knowledge graph that is a way of structuring information about the products that it's trying to sell online, about how it advertises or markets those products, how it relates those products to the needs of consumers. All of this is stored in knowledge representations that are usually considered company secret, that are not necessarily available for us to peruse, but are incredibly important to be able to access information that are used by companies. And we're increasingly seeing initiatives on the part of NSF and NIH and other funders to create knowledge graphs that describe what we want to know about various areas of scientific endeavor as well. And I think what's very exciting to be thinking about is as we make our data better, as we make our metadata better, as we begin to build knowledge graphs to describe what we know about in science, we're increasingly going to be linking knowledge graphs to the scientific data that we put in our public repositories. So ultimately, the graphs will provide us with detailed information about what we know about the world. We'll be able to link those graphs to the data that are now going to be much more accessible in online repositories, and we'll have structures that both people and intelligent agents are undoubtedly going to be able to access to understand how do concepts in those knowledge graphs get supported by scientific data. What are the ways in which we can search our knowledge and our graphs, our knowledge and our data to discover new relationships? And how can we understand how our conclusions about the world are supported by data that we can actually examine, because those data not only are linked to the graphs, but the data themselves have better metadata that allows us to understand what experiments were done in the first place. So where is this all kind of leading? Well, I honestly believe that within our lifetime, we're increasingly going to see scientific concepts formalized in terms of ontologies. And that ontologies and terminologies are going to be used to standardize scientific communication in ways which we simply don't have right now. Rather than being excited about our ability to publish our scientific results in journals that have only one name in the title, we're increasingly going to see an effort to try to disseminate our work as data and as knowledge that people and machines can access in ways which are simply impossible when we view the primary output of our scientific work as PDFs. And when we link our knowledge and our data through knowledge graphs, we're going to be in a situation ultimately where we're going to start disseminating scientific results in a way which makes them machine interpretable, and it's going to make knowledge and data basically support new kinds of learning activities that we simply haven't seen before. And ultimately, I believe that once knowledge is disseminated this way, we'll have technology like Cedar that can facilitate the publication of data in a way which is not really easily done now, where the scientific results are understandable both to people and machines, making intelligent agents able to surf the web, if you will, and search and read the literature, integrate information in ways which we can't do right now, track scientific advances because our intelligent agents will know what data to look for, and the metadata will be sufficiently adequate to inform those agents about what experiments were done. We can track scientific advances. We can have our Siri-like systems tell us when we should be doing a new experiment. They can tell us when we should stop doing an experiment because someone else has already scooped us. We can re-explore existing data sets, and they can suggest to us what are the new experiments to perform. And when you look at some of the work going on in robotics, our agents may even look at the literature online and maybe do those experiments themselves. Anyway, that's the future that I see coming. To get there requires fair data. To get fair data requires the ability to store information in a way which makes it really accessible. That means using ontologies whenever possible to describe the terms that are important, to standardize the metadata so the metadata are actually useful, and most important, to get the scientific community engaged so they recognize that the way to learn the most from their work is going to be not by reading journal articles, but by having intelligent bots go out and access data and knowledge over the web in a way which is meaningful both to people and to machines. Thanks.